About binomial data, but before we start, there was a quick question asked about the assignment, so I thought I'd go over that just a little bit. So for the assignment, I guess the scenario is that you have a bunch of data for weight, and say these dashes are the women, and I don't know, the sideways dashes are going to be men. So you have two groups of data, and the generative model for this data is that there's both populations are drawn from a normal distribution. There's a mean for, I guess you could think of it as there's a mean for women and there's a mean for men. We don't know, though, if these are equal or not. So we actually reparameterize it as a center point, so an intercept, and then well, let's just call it delta for a difference between men versus women, male, female. So the model of the code that you have has the intercept difference parameterization. We also estimate what the variability of each group's distribution is, but we have that as an unknown. We're estimating that from the data. So we've got 1, 2, 3 parameters that we're uncertain on.
Why we are taking the difference male minus female? Can it be reversed?
You could, yep, exactly. The direction of the difference simply changes the sign of that parameter. So and it comes down to when you create that column that translates male into either plus 0.5 or minus 0.5 and female into the other one. It just matters. The sign that you put on the plus 0.5 and minus 0.5 determines the direction of the difference that your code is doing. So yeah, it only changes the sign of this parameter, the delta, the difference parameter. So we've got 3 parameters on which we're uncertain. And I asked you guys to do the analysis 3 different ways. One way where you use your intuitions for where sort of people's weights are generally and what the difference is between men and women generally. So let's actually start drawing out those. And I need to remember not to put the paper under. Okay, so if I were doing it, and I wanted to talk about the intercept, this is again weights, I'd probably center it somewhere around, sure, 165. Sort of a nice midpoint between men and women, but I'd maybe believe it to be sort of if this were 180 and this were 150, I'd maybe believe those a little bit. Probably wouldn't believe a mean of 200 or a mean of, what's the analogous? That's 15 and that's 20, 15, 130. So I formed a distribution that sort of generally looks like this. To parameterize this, to sort of make this a shape that we can talk about easily, we could talk about a normal distribution with mean of 175 or 165 and a standard deviation of, I don't know, to make that reasonable, I don't know. What do you say? So standard deviation of, say, 30. You can actually plot this out in R to see what the actual distribution would look like for you. So that's for the intercept. For the difference, so I'll say the delta. I'll use a normal distribution again. I think that men and women differ by, say, 40 pounds. So that's my peak credibility. I still have some credibility down to, say, 20 and up to 60. So I'd maybe sort of have a normal distribution that's kind of like that, drawn poorly, of course. So the mean here would be 40, and the standard deviation for this one would be, I don't know, 20.
If I understand correctly, we usually assume the difference is 0, so we can really see the posterior whether there's a really different or not.
Yeah.
Right?
So that's where the second one is. This is what you actually would expect. So this is number 1. I asked you to do it 3 different ways. This is number 1 way. I will talk about what you're talking about for number 2 way. Okay, so this is for, we've got the intercept and the difference, and the last thing, parameter we're uncertain about, is that sigma variable. Maybe I have peak belief in a variability of, I don't know, 30 across people. I shouldn't believe anything that's below 0, so I need my belief distribution to sort of drop down to 0 here. I might believe 60 a bit, might believe 90 a bit. So I want a distribution that has sort of a nice shape like that. And to achieve this, we can use the log normal. So
Log normal is going from 0, 1, 1 is 1 standard deviation, right?
that's if we've standardized. We haven't standardized yet.
So can you explain that a little bit more? I get confused. Yeah, between normal and scale for.
Okay, so for as it is, I haven't told you guys to scale the data at all, and I've told you to use your sort of true priors. So for expressing this, I'd say this is a log normal with a peak of about 30 and a variability, I don't know, that looks like about 10. It's easier to actually just get a sense of these curves by plotting it up in R. Let me actually do that. So.
With variability, where are you measuring to? So again, it's from the mean to.
Well, so what this curve actually is, it's as if you take a normal curve, something like this, and you exponentiate the x-axis. So exponentiation means everything from 0 to 1 gets, everything that's in the negative domain gets squished into the 0 to 1 part of the x-axis, and everything above 0 gets increasingly pulled out. That's what the inverse of a log does. Log will take all the numbers from 0 to infinity and fit and sort of pull them out so that you go from negative infinity to positive infinity. The reverse of that is to take everything from negative infinity to 0, squish that into 0 to 1, and then take all the values from 0 to positive infinity and start increasingly stretching them out. So log normal is just a normal with some mean and some variability that's being turned into, translated from the log scale, log of x, to the regular scale where this scale is x.
Sorry, I think my question is more basic than that.
Yeah.
What is variance?
What is variance?
Again, it's the spread of the curve.
Yep, it's literally
to where.
So just in a normal distribution, say even if we're talking about up here variability, it's hard to. Let's actually. I'm gonna open up our studio and start drawing curves here. Where did our studio go? Okay, well, I guess I have to say new session.
And like, what is the meaning of the values that fall within the variance versus the ones?
Most values fall within a sort of two So the number that we use here, let me put this so we can see it on the screen and make that go away. And I will make this a little bit bigger. So if I generate a bunch of random numbers, so I'll store them in something called X. I'll use our norm to generate 1,000 numbers. There's a mean of 0, and a standard deviation of 1. Standard deviation is just a square root of the variance. So I'll generate those numbers. They've been generated. Now I'll plot a histogram of those numbers, and I'll make sure that there's, say, 100 breaks. So you notice like most of the values fall within about 2 units of standard deviation, where unit standard deviation is 1. So most of the values fall between -2 and 2. If I generated data such that this value were, say, 3, then all the values still fall within 2 standard deviations, but this time it's a standard deviation is 3, so it goes from -6 to +6. So you can think of it as sort of 2 of these reflect sort of where most of the data will fall. You'll get a little bit outside still, spilling outside, but it sort of sets the range over which you'd observe most of the data.
So there's no, most doesn't mean anything.
Well, if it's something like, you can actually get it, what is it? P norm 2, actually, what is it? If I say -2, 0, 1, that will give me an essay times 2. So this is saying what proportion of the data fall from -infinity to -2 in a normal distribution with a mean of 0 and a standard deviation of 1. So if that's saying what falls, again, let me put this back down to, say, 1 and do a histogram. What proportion of the data falls from -2 below? If I want to also ask what proportion falls from +2 above, it's 2 times that value. So that will say what proportion falls outside the range -2 to +2. If I want the proportion that's inside the range, I do just say 1 minus. So 95% of the data fall within 2 standard deviations of the mean. So that's what I mean by most.
Okay. So as your variance shrinks, it means it means basically 95% of your data is falling within an ever smaller range.
Yep.
Okay.
Yep. Okay, so let's imagine, though, that instead of just taking X, we generate random data, but then exponentiate it. What will that look like? This is the log normal distribution. So this is again, the raw scale X. It'll be normal on the log scale. In fact, here, I'll just create another thing. Log of X, that's just the name, equals that. Oops. So if I were to generate this data sort of on the log scale and plot it, looks normal. If I were to then exponentiate it to bring it from the log scale to the real scale, it has this log normal distribution here. It's a little hard to see because the range goes out so far. If I do from equals 0 to equals, I don't know, 5. I guess I have to say xlim equals C 5. There we go. And I'll say BR equals that. So you get this is a fairly broad value distribution. you can actually see the curvature a little bit better if I have something like a normal on the log scale with a mean of 0 and variance or standard deviation of 0.5. That yields a distribution like this. Most of the data is now between, it didn't run that first one. Yeah, run. So now most of the data is between -1 and 1 because the standard deviation is 0.5. Exponentiate, whoops, and plot, and now you get sort of this positively skewed distribution. Its peak is at about 1 because that's what the that's what exp of 0 is 1. So it's peaked at 1, and it has this sort of general variability here, but a positively skewed shape. Another way to visualize these curves that I showed you the other day, but this sort of makes it clear that you're first doing a normal on a log scale and then exponentiating. A way to get a nice pretty curve, though, is to use the curve function, and you use dnorm, but you log everything on the inside. And have to tell it from equals 0 to equals 5. This should plot sort of the same sort of outline as this, but as a curve. Oh. And curve, dnorm. Pardon me? I actually can, a trick in our studio is you get anywhere within sort of a block of code, you can hit Command Enter and it will send the whole thing. It's the same as selecting the whole thing, but what's going on? Oh, I don't want log of 0, I want log of 1. 1 being the, so actually, I want 0 and 0.5 not logged. So that looks the same as the outline of that hist x. So yeah, back to the original example. We wanted to get a curve that, open up the camera. We wanted a curve that sort of peaked at 30 and had sort of a general variability like this, such that we still had a little bit of support at 60, but not so much at 90. So if I wanted to actually do that, I'd just play around with what values I have to put in here. So if I put, it's useful to start logging things. So log 30, and I don't know, I'll put that. Oh, and it can't go from 0 to 5. It needs to say 0 to 100, for example. So that has a peak at 30. It's hard to see, but it's way too, like there's way too much support still out here. So I'll maybe put 1 on there. Still too much support out there, say 0.5. That starts being a little bit closer to what sort of I had in my picture. 0.3. So if that truly, so that's much closer to what I had in my picture. If I truly had sort of a peak belief in a variability of about 30, but I still thought 60 was sort of reasonably likely or believable, and I thought 20 was reasonably believable. Having a log normal with log 30 there as the sort of center parameter of the log normal, and 0.3 as the other parameter of the log normal, that would be reasonable. So yeah, that would set all the values. Let's actually go back to the drawing. So here I'd say log normal, and so log 30, comma 0.3 would be a good sort of set of parameters to specify to represent my credibility for where sigma is, having not seen any data yet. So that would be sort of the way I'd approach question 1. Question 2 says use the same sort of set of beliefs, but for the difference parameter. Yeah?
So log 30 equation is a bit different, isn't it? Because we are thinking about standard deviation is 30. So we need to put something that will get close to 30 after giving log something.
Yeah, so that's why you say in a log normal. So remember the numbers inside the call to log normal in stan assume that you're on the log scale. So I want it to be peaked at whatever turns into 30 on the raw scale. So I say log of 30, and that yields the number on the log scale that corresponds to a peak on the raw scale of 30.
We actually can write within the brackets of log normal log 30.
Yeah. Yep. And 0.3, that is the value on the log scale that I want that eventually yields this nice curve. So, so the second question says, okay, use your same sort of priors. Still don't standardize the data, but use a skeptical prior where you've taken the thing that you're interested in, the effect, and you've taken your prior and shifted it over to be centered on 0. So instead of mean of 40, for the second one, I'd say a mean of 0. And it says make a broad variability. So what do I mean by that? Well, probably would make sense to make it so that like the thing you thought was most likely still fell within the curve. So I don't know, making it so that the S, the variability, was equal to the value that you wanted. So if you wanted it at 60, I mean, if you put it at 40, that means that, again, 2 times the variability still, 95% of the curve will still fall within 2 times the standard deviation. So if you put the standard deviation to the value that you actually thought was most credible, it will still be pretty near it will still be considered fairly likely on that curve. So actually, and let me just plot that just to, so I'm going to grab this, and so and I'll say from negative 100 to 100. So our original, and this is not using a log normal, so we don't need to do logs. So just x. Our original one was 40, and what did I have? 20. So that looks like this, peaked at 40. And what I'm saying is to shift it so it's 0, but still has 40, that 40 value as relatively. So that would be a relatively broad prior centered on 0. So shifting, going from that to about that. And this all depends on what you set as your own personal priors at the outset for the first one. But a general strategy is whatever you put here in the first one, put it here in the second one. And put 0 there at the second one.
If you must.
Well, you don't have to.
So for the second one, you'd leave your mu intercept the same as what you did in the
Yep.
first one?
Yeah.
But can I go above that, like 50 or 60, because you go with more data, like a bit more broad, isn't it?
Sorry?
So if so mu intercept is
Okay, if you want to make your
broad,
sure, yeah.
or
Then you're changing more about the model than what I wanted to highlight. What I wanted to highlight with this is that when you go from what you might reasonably believe as an experimenter, having been motivated to do this experiment, to the skeptical prior, what changes in the conclusions you make? Ideally, not much. If you've made it so that this second prior is relatively broad, then not much will have changed. So when you start changing this stuff, if you start making this broader, it actually, again, will make it not, you won't get much difference. So that's not harmful, but just in the interests of experimenting with different priors and their consequence on the posterior, it might make sense to just change sort of one thing at a time. And the third one should be relatively straightforward since we did it directly in class with one of the examples, and that is you standardize the data and then you use the sort of default priors of 0, 1 for all the parameters. So normal 0, 1, normal 0, 1, and then log normal 0, 1. All right, so what we're going to talk about today is binomial data. So far we've been dealing with the idea that we observe data on some continuum for outcome variable y. So sort of we might have data that's all like this, and we characterize that by saying, okay, our generative model is that there's some normal distribution with some mean that we are uncertain about and some variability that we're uncertain about. But oftentimes we just have non-continuous data coming in. So you have just for a given person, they just give you a 1 or a 0. So if you have, say, 0 here and 1 here, you get a bunch of people with 1s and then a bunch of people with 0s. It's actually easier to visualize this by just having the data as, okay, this person gives you a 1, this person gives you a 1, this person gives you a 0, this person gives you a 0. So it's sort of a data frame type format.
Categorical data.
Yeah. So this specifically is sort of a special kind of categorical data where it can only take on 2 values. So I emailed you guys out a data set. It's a zip file. When you unzip it, oh, I actually did open up this already. Okay. So when you unzip it, it should be a folder, binomial underscore data, that has a bunch of files inside of it. It's got 2 data sets, binom1.csv and binom2.csv. So there's 2 different examples. There's also 2 R files, but they're empty. So I just put them in there so that it's easy for you to sort of initialize by opening up the single file. And this is where we'll start writing our code. So before, though, we get into talking about this data, well, actually, let me just show you sort of an example of this. So I'll say view file. So here's an example of binomial data. You've got a column called died. So presumably each row is a person, and this column encodes whether they died or not during the experiment. This column is group. I see drug for a bunch of people, 30 people, and placebo for a bunch of people. So this we can presume is the results from a study where it's drug versus placebo, and we're trying to establish whether giving people the drug versus placebo improved their survival in the experiment. So presumably it's some sort of high mortality disease, and we're trying to reduce that mortality. So we've got this sort of list of 1s and 0s. Let me go back to my drawing. And it probably doesn't make sense to start talking about like normal distributions on each of these things. So what typically is done, you can think of, for a given group, the set of 1s and 0s that it has. If you take the mean of the 1s and 0s, that computes out what the proportion is. So P for, I guess, drug group. And if you had another sort of set of 1, 1, 1, 0, 1, 0, another set of, you could talk about the proportion for the control group. So now we're talking about proportions. Proportions, again, fall on sort of a scale from 0 2, 1. But now we can start talking about sort of variability along this scale. So if one group had, say, a proportion of, say, 8.5, or say 8.8, its value would be right there. Another group had a value of, say, 0.5. Its value is right there. And maybe these are the two proportions you observe. I can't actually remember what we have in the data set that we'll deal with. We'll take a look at that in a moment.
Proportion of 1, right?
Yeah, well, the total, if these were all 1s, the mean would be 1. So the highest you can go is 1. If these were all 0s, the mean would be 0. So the lowest you can go is 0. So it's a sort of constrained, it's a constrained scale from 0 to 1 that we're dealing with. So if we were to observe a whole bunch of observations, we presumably would be able to sort of compress each group into its own proportion. So maybe this is the proportion control, or maybe that's drug. It might make some more sense. And this is proportion in control. So this is whether they died or not. So hopefully we have a result like this where the drug keeps more people alive than the placebo does. But what do? We just have two numbers now. How do we do any sort of stats? What sort of, if you were to encounter these two numbers, what would you sort of start thinking you need to do? Or
With the Bayesian method or with other methods?
oh, well, you can talk about other methods. Any
Chi-square.
chi-square. Okay. Yep, that's one way of doing it. That is a form of categorical data analysis. Any other? Let's see. If I told you that these two numbers, the sample sizes contributing to these two numbers were, say, just this: 1, 2, 3, 4, 5 in this group, and 1, 2, 3, 4, 5, 6 in this group, would you be very confident in that this is a sort of a real difference? No. Not super confident. But what if I told you that this proportion was from 2,000 people and this proportion was from 2,000 people? You maybe would start being a little bit more confident. So yeah, we can't just look at these numbers. We need to take into account sort of how much sampling effort yielded those two numbers, what the sample size were contributing to those. Now, that's where, with chi-square, you get into when you look at your lookup table, you say what degrees of freedom you have, and that will help determine that. What's nice about the Bayesian approach is that it will sort of automatically figure out how much sampling effort was done. So our generative model, though, a very common thing to do is to have a generative model as follows. You say that each group has, let's see, what would be the best way to put this? So ultimately, it would be nice to be able to get to a scale where we can start talking about normal distributions, because we're used to thinking about normal distributions. So the normal distribution is usually defined on the, wow, those are really bad infinities, on the negative infinity to positive infinity scale with some distribution. So it actually goes up to negative infinity to positive infinity. But when we're dealing with probabilities, they go from 0 to 1. So a really common sort of transform to get from this to this is what's called log odds. So what is odds? If you've got a probability here, let's just call it P. Let's say it's 0.6. When you go to the racetrack, which I'm sure you all do, you can talk about what are the odds associated with given bets or given winning. So what are the odds? So usually it's something in something. So it's some sort of ratio of two things. So odds is equal to the probability divided by the remainder of the probability. You can also think of it as probability of success divided by the probability of failure. So you see that if we have 0.6 there, the odds are going to be 0.6 divided by 1 minus 0.6, same as 0.6 divided by 0.4. So that's going to be a number where, let's think about what is the range of this new scale, odds. So here we can talk about probabilities or proportions, but when we switch to odds, what is the new scale? So we can imagine, sorry, go ahead. So what is the domain of this new thing? What are the possible values that you think that this one can take? We got 0 to infinity, so it can't ever take negative numbers, right? Yeah, okay, so this new scale has at least made it so that instead of from 0 to 1, we're now going from 0 to infinity. And that's sort of clear by the fact that as p gets bigger, the thing on the bottom is going to get smaller. Whenever you have a big thing divided by a very small thing, that gets to be a very big number. But as p gets smaller, closer to 0, the thing on the bottom is going to get bigger, so that as you have a small thing divided by a big thing, that's going to get closer and closer to 0. But eventually, just if p is 0, then the bottom thing is 1. 0 over 1, that hits 0. So you go from 0 to positive infinity with this, and conceptually, it's not clear sort of why people decided to do this. It just makes the math work out really nicely. People decided that it's still not enough to have this hard bound at 0. So what people do is they say log. Well, here, I'm actually going to do a new piece of paper. So if you've got...
We use a lot to avoid having a negative number.
Well, before we used a normal distribution on the log scale that gets exponentiated to get back to... So the log normal is a normal distribution on the log scale that is then exponentiated to make it so it's 0 to positive infinity. We're doing the opposite here. We're going from a scenario where we have proportion is 0 to 1, odds is 0 to infinity, and now if you do log of odds, it makes it from infinity to negative infinity. Positive infinity. So this is when you actually see sort of analyses out there of binomial data, if they're not using just simple chi-square type statistics, if they're actually doing what's called the general linear model, most often they're talking about value. They end up doing inference on values on the log odds scale rather than values on the proportion scale or the odds scale. That's because you can have a nice normal distribution on the odds scale where they're not being truncated by 0 or at 1. Or sorry, the log odds scale, they're not being truncated at 0 or 1. So let's actually work out. So if we had a proportion of 0.6, the log odds is 0.6 divided by 0.4, so that's what? Anybody off the top of your head?
1.5.
Okay. Oh, right, of course. Yeah. Yep. No. Oh, okay. So that's 1.5 on the odd scale. So can you do the log of that?
No.
No, you can't.
Yes, I can.
0.4 ish. So back to our camera. So we'd start out with a value of 0.6 on this scale. It ends up being 1.5 on the odds scale. So on log odds is about 0.4. To give you sort of a feeling for how this works, if it were 0.5, it would be log odds of 1, odds of 1, so 0.5 divided by 0.5 is 1, and therefore on log odds it's 0. If it were 0.4, well, if 0.6 over divided by 0.4 is 1.5, it would be 0.4 divided by 0.6, which is 0.75? Wait, yes. 0.6 repeating. But on the log scale, that ends up being negative 0.4. Let me triple check that. So if I say 0.4 over 0.6, 6 repeating, the log of that is negative 0.4.
What would be a question that I could use this to answer? I'm sorry.
Yeah, well, we're going to get there. Yeah, we're going to get there. One nice thing about that is when you're thinking about log odds, 0 is about 50%. And it's symmetric around 0, such that if you go this is 0.1 away from 0.5 in one direction, that yields this number. The equivalent movement in the opposite direction away from 0.5 yields just a number that's negative that value. All right, so this is the log odds scale. This is going to be the realm on which we have our priors and any like effects that we have are going to be in this. We can always convert back to the proportion scale. This, however, is just the general domain that most statistics that use binomial data will talk about. So let's actually, to give you a better sense as to like how this works, let's actually use the example that I gave you. So we've got this binom.1.csv. We need to read it into R. So it's here in our working directory. I'm going to double check I set this. No, I didn't set this to my working directory. So set as working directory. So in my R file, I'm going to create a thing. Maybe I'll call it dat and read I guess I can just use read.csv. Read.csv is one of the built-in functions. I taught you about read_csv that comes from the reader library. That's a little bit nicer, but just for convenience today, we'll use this one because even though read_csv is nicer and smarter, I've structured this data so straightforward in such a straightforward manner that read.csv, even though it's dumber, will be fine. So having read in dat, I can double check my environment and see that it looks exactly like it was in the file. Bunch of ones, bunch of zeros. I can actually see what is the sort of mean, what is the rate of death in my samples overall. So mean dat died will give me the proportion. So overall, about 80% of people died. If I want to look at each individual group, maybe we do dplyr. So I'll say library dplyr. And I'd say dat, pipe it into group by, and I'm just grouping by the other column that's in there, which is group. And summarize. And maybe I just want prop guide. So this will spit out a little table. Oh, I need to run this first line of the proportion that died in each of these two groups. So there's drug, there's placebo. So happily for the investigators, it's in the direction that you might expect. Placebo having a proportion dying of about 0.9, 90% of people in the placebo group died, but only 70%. But we don't know if that's sort of a difference that we might consider worth changing our, what might be a nice skeptical default belief of no difference. So we need to do some Bayesian data analysis. Let's take a look at, first of all, the continuous.stand that was in the folder there. I'll open it up, but pop it out so that it looks nicer. And pull it over. So this is what we used to use for continuous data. So we'd read the data in. This is what we had for the last version of continuous data, where we had the data looking kind of like this, where we had both groups in one object, one column that encodes sort of the outcome, another column that encodes the group. So we have a thing called y that we're passing in, that's whatever length the data set is. And another thing called x that we're passing in that was a list of, sort of a conversion of the group name to just a number, either negative 0.5 or positive 0.5.
So we're using the continuous instead because we have the log of there.
Well, I'm just describing right now what we used to do, and so that I can contrast with what we're going to do with the now binomial data. So we'll have to remember to create this thing called x that converts this column group into negative 0.5 and positive 0.5. Let's actually do that right away before I forget. The easiest way to do this, and I think I had this as code in the 06 folder that we left off with last time, but is to create, so when we were talking about dplyr, I showed you using mutate to create new columns. It's actually a little bit faster in this circumstance to do it without even bothering using dplyr. We're going to, again, create something and store something. So that's what the equal sign is going to do. It's going to create something on the right of the equals. It's going to store whatever it creates on the right into something on the left. So I want to put something into dat, but specifically put it in a new column in dat. So dat dollar, I'll just call it group as num. So creating what this is going to do is it's going to create a new column in the dataset dat and name that column group as num. So what's it going to put into this new column? The result of whatever I've asked it to do on the right, which we're going to use the if-else command. So what this is going to do, if-else accepts as its first argument a logical test. And if that test comes out true, it will put one number. If it comes out false, it'll put another number. So I want it to test whether the content of the column dat group, so the group column within the dataset dat, is equal to, and I had what, drug and placebo. So if it's drug, I want it to put a negative 0.5 there. And if it's placebo, I want to put it, if it's not drug, it will just do this one. So the corollary is that this is going to be what's put in placebo. So it's going to go through every item, every row in the column group and ask, is it drug? in that column? If it is, it's going to put a 0.5 in this group as num column. If that item isn't drug, it's going to put a positive 0.5 in that column. So if we run that, and if we just look at that, we can see that wherever there's drug, there's negative 0.5s. And whenever there's placebo, there's positive 0.5s. So there's our indicator column that the stand file is going to expect as encoding the two different groups. So again, thinking about this file here is when we're talking about a generative model that was using expecting continuous data. We had a parameter called, well, here's our generative model down here, saying the continuous data y is modeled as normal. It had this variability sigma that we had a prior on. It had a intercept of mu, but what was added to the intercept was contingent on what the value in this indicator column was, such that if it was one group, it would be diff times negative 0.5. If it was the other group, it would be diff plus 0.5. Or sorry, times plus 0.5. So that made it so that we're moving away from the intercept to one of the groups or to the other of the groups. And of course, we've got a prior on the intercept and a prior on the difference. These priors were set, these priors are there just sort of expecting the data to have been standardized in the first place, hence the normal 0, 1. So let's see what the stand code for binomial data would look like. Let me, yeah, that doesn't look great. So I'll go Files and Binom, and I'll pull it out. And screen and bake. So it's actually a little bit shorter. So here there's total 16 lines, and here there's 14 lines. So we've lost 2 lines somewhere. The data structure coming in is the exact same. We've got the total number of data items, a list of the outcome, and the list of the predictor variable, the indicator variable. We now have 2 parameters that we're uncertain about, whereas before we had 3. And down here, for our generative model, we had y is distributed as normal something. And here we've got y is distributed as Bernoulli logit. Okay. I told you about log odds. Another term for log odds is logit. Bernoulli means the transformation from logit to probability. A Bernoulli trial is whenever you have something where you can define a probability, like flip a coin with a probability of that being heads, and then the inverse of it being tail, or the 1 minus that being tails, and that will yield a 1 or a 0 outcome. So this Bernoulli logit means that it's expecting the data to be 1s and 0s, with a probability of 1 being the log odds specified in here. So if we were to actually have just Bernoulli, it's expecting on the inside, whatever's on the inside, to be sort of referring to the probability. Bernoulli logit means that it's automatically going to convert from this being a logit value through the sort of backwards through the steps that we took here to get from log odds back to a probability. So we still have, though, the mu and diff type parameterization. So that's going to be common to the continuous example. So this is an example where we are, again, comparing 2 groups, drug and placebo, on ultimately whether one affects the likelihood of the whatever outcome this is, and we had it as death. So having that mu and diff parameterization, mu reflects what is the overall sort of probability of death regardless of what group you're in. And diff reflects what is the effect that the grouping had, whatever caused the grouping, that is receiving drug or a placebo, what is the effect that that manipulation had on the outcome. Now, as we experienced before, setting priors kind of depends on your expertise with the domain of the data. When we had like continuous data and say it was IQs, we had some intuitions about IQs. With weight, you guys have some intuitions with weight. We're talking now about parameters that exist on the logit scale, and you guys probably don't have a lot of experience on the logit scale whatsoever. So maybe you want to standardize in some way to make it easier to set these values. Happily, you can think of logit sort of when you do a binomial analysis, the data is already pre-standardized. It's ones and zeros, such that a sort of variability of normal and 1 on the intercept is actually a pretty decent number, and a diff of normal 0, 1 is also pretty decent. That is, that actually comes a little bit from my experience in the literature where you rarely get a difference between conditions of more than 1 log odds unit. That would be fairly substantial. So you can actually use sort of the normal 0, 1, normal 0, 1 on both of these as relatively acceptable default priors. And so let's actually go back to our data file. So if we wanted to compile this, library rstan and model equals stan model binom 1 dot, or just binom dot stan. Whoops, I need to say this line, then this line. There's a problem.
Because there's 2 stan documents, that's what happens when...
Ah, no, that's not the error here. It actually read through the thing, and I remember what I did wrong now. The stan doc, so you'd have to change this in the stan document. It doesn't want this to be a vector. It's kind of annoying. It wants it to be, you have to change this from vector NY to int, and then y NY. It's really annoying that it doesn't automatically do that. Pretty sure that's the reason why I got that error. Let me run it again.
Why is it instead of real?
Pardon me?
Why is it not real instead of integer?
Because it's expecting it to be a Bernoulli outcome, which is only 0 or 1. So that's compiling. So while it's compiling, I'm going to write the code for what I want as the sampling. So I'll create an object to store the posterior samples. The sampling function from rstan takes 3 arguments, 3 main ones. I haven't packaged together the data for stan, so I should do that. Remember, we have to put it in a list. It wants 3 things, ny, y, and x, but those are just the 3. Well, ny is just the number of rows in my data set, dat. It needs to be n capital Y, matching the capitalization we had in here. Y is the outcomes, so it's dat died. And X is that group as num thing we created. So we're packaging up the data for Stan in the format sort of it expects, NY, Y, and X. Oops. And having run that, oh, not n rows, n row. Having run that, I can say data for Stan. It's the thing I want to supply as the data for this sampling. And I'll say seed equals 1 for being able to replicate this down the line if I ever come back to this project and want to run it again. So I should be able to run that. It will run super quickly. This is a super fast model. It's done 4 chains by default, 2,000 iterations on each chain. So let's take a look at the output. Before I do that, I'm going to expand this. So I'm immediately going to look at our hat. It's all 1 and NF, number of effective sample sizes, or effective sample size is what this is, and they're all above 1,000. So I can now look at the stuff on the inside. So we've got the 2 parameters, diff and mu. Mu being where in general is the data on the log odds scale. So 1.35. Remember I said 0 on the log odds scale is 50%. So 1.35 means that it's more than 50% is the likelihood of death. What would this translate into actual probability? Well, to actually go backwards through the process, a quick trick to do that is to, I'm just going to make this bigger so it's up higher, pull it over a little bit. Is the plogis command that converts from the log odds scale back to the probability scale. P means you're going to get probability afterwards. So you say plogis 1.35, and that's going to spit out whatever value is right here, 1.35, that's the corresponding proportion. Now, way up above, we actually asked what is the mean of the outcome, and we got 0.8. So our posterior has actually yielded a value for the mean outcome that's pretty close to what we observe in looking at mean dat y. Not del. Oh, it's died. That's what it's called. So our posterior seems to be peaked around where the data is. If we want to actually get what is the credible interval. Now you can report all this stuff in your reports on the log odds scale. Most people that are into sort of the domain in which this takes place, the general linear model, this kind of data will be familiar with log odds enough to make that as the sort of thing that you're reporting. So you could say log odds of death was 1.35 with a 95% credible interval from 0.73 to 1.97. If you actually wanted to convert all those to probabilities, that's fine too. So in the same way that we converted this sort of peak or the mean of the posterior using plogis, we can do the same with the 95% credible interval. So let's see, take this value, 0.73, say plogis 0.73, and plogis, what is it, 1.97. So I'll run off, well, we already did the 1.35. So the 95% credible interval on where the groups are regardless of their group label, just the general outcome of death was from 0.67 to 0.88. So you could report that. Now, the thing that you're most interested in is whether the groups differed. So the posterior has our sort of mean of about 0.89. Let's look at the 95% credible interval. It ranges from about -0.1, -0.2, up to about 2. So, yeah. So critically, 0 is sort of in this range. So 0 is still relatively credible. We can actually plot this out. Stan hist par, oh, we have to say, out is the name of our object. What does Stan hist name the first argument? Hover object, okay. So we'll look at the diff parameter. Oops, par. What have I done wrong? Stan hist. I just do out. I don't know why. Anyway, this is a plot of both parameters. 0 as the amount of difference is still fairly credible. Now, this is on the log scale, but 0 on the log scale for a difference is the same as 0 on the probability scale for the difference. So 0 is still fairly credible, so you might, if you need to sort of make a dichotomous decision about whether this treatment was effective or not, well, you don't, I mean, you tend to have more credibility for positive values for an effect, that is, that the drug decreased the mortality, than negative values. So that might motivate further study to maybe narrow up this credible interval, gather more data to be more precise in what you actually believe. But if you had to make a decision, 0 is still fairly credible.
Is it similar when the confidence interval touches the 1 and it's like not as good as it's away from? The down of the difference does not come on the 0. It goes all the way to the right. Would you still consider which one is more positive effect of the drug? You know, when the confidence interval that touches the midline, like, and not in the Bayesian method.
Mm-hmm. Yeah.
If the confidence interval touches the midline, that means it is not a good drug.
Yeah, I mean, the way most people actively interpret confidence intervals is how you should interpret credible intervals, in the sense as like reflecting the range of reasonable values over which you could believe the true value lies somewhere there. So that interpretation, say this whole thing were shifted over 1. So think of this as 0, this as 1, 2, 3, 4. That outcome, if that were our outcome, would convey that 0 is actually not very credible. And these other positive values were much more credible, in which case I would sort of, if I had to make a one-off decision, I would decide that this drug works and I'd start using it in my patients. So that's a scenario that would say that 0, again, pretending it's over here, would be excluded by the credible interval. The 95% credible interval would probably be sort of from about here to about here. Yeah, maybe we'll have to draw out the thing.
Yeah, basic question was, what is the difference between confidence interval or credible interval?
Okay. The credible interval is what you guys think the confidence interval is, or at least what most people think the confidence interval is. The credible interval reflects like the range of values that contain most of what is believable. A confidence interval is an interval that if you were to use it across your lifetime, 5% of the time it would fail to capture the true value. It doesn't have anything to do with, in a given experiment, what you should believe. It just means across your lifetime, 5% of the time, this will fail to capture the real value in that corresponding to what that experiment was looking at. So it's conceptually not very straightforward because it talks about the long-term run of like across your career. Whereas the credible interval says, okay, given what you sort of established as the sort of what you believed at the outset through your priors and what the data forces you to update your beliefs to, what is sort of the reasonable range of beliefs now?
For this study, like
For this, yeah. What has this data forced you to update your beliefs to? So if we had more data, the interval would narrow up and you'd be more confident about something. Now, presumably, if we had more data and there truly was a difference such that one was, I guess, what was the, let me pull it up here. If 0.89 log odds of a difference of 0.89 were the true value, and we were to collect more data that were consistent with that value, we'd end up having a credible interval that eventually started to sort of exclude 0 as a credible value. But it just so happened in this case, we didn't have enough data to have a narrow enough sort of set of beliefs to be confident enough about a non-zero number.
So I have a question about priors. Let's say you did this drug study last year, and then you did it again this year. When we're analyzing it, is the prior going to be the drug study you did last year? Or is your prior going to be an arbitrary belief, and then you'll compare those two to the...
Well, it depends on how you want to communicate it to others. If you want to do sort of a true sort of meta-analytic approach where you're saying I want to use the information from prior studies to I want to reflect that there is information from prior studies and I'm just trying to update that information with my new data, then yes, you would set whatever you found as the as the result for the intercept as the sort of peak thing that you believe for the new experiment, and you put the result from the prior experiment difference as the peak difference that you believe here. Then you'd run through the experiment. If you wanted to publish just the second one, you'd maybe shift the prior on the difference back to 0 to be sort of more skeptical. But yeah, you can actually even add the data, add them all together, and that would be effectively the same as starting out with a uninformed prior or a weakly informed prior, and then adding things together
So prior
afterwards.
data would still go into the data section. It wouldn't.
Yep,
It wouldn't.
that has
ever
the
go
same
into the
outcome.
model.
Yep, that has the same. You get the same results if you added all the experimental data together in one, call it one trial, and used weakly informed priors at the outset, as if you did it once for one experiment, established what sort of the posterior is from that experiment, and used the posterior from that experiment to motivate the choice of priors for your second experiment. You'd get the same results no matter which way. Indeed, the way the Bayesian data analysis works, you can actually run it every time you get a new sort of observation from your study. You don't need to worry about waiting to the end. It will update even single observations using, and it's, yeah. I won't go into that, but yeah.
But generally, like with scale or standardized data, when there is no previous study or experiment, so we don't have any.
Yeah. If you don't have any strong beliefs either way, I mean, particularly with regards to the intercept, like we might even observe in this data the mean was 0.8. When we looked at the, let's see, we said what is the mean amount of mean attrition is about 0.8. So if we wanted to actually center the data, to accept that as sort of a good prior for the actual data itself, we could actually figure out what is the log odds value of 0.8. To get that, you would use QLogis. That converts a probability into a log odds. So the QLogis of 0.8 is 1.3. So instead of normal 0, 1 here, we could put 1.3 in 1, and that would start us out. Say that 0.8 came from a prior set of studies that established what is the mortality in this disease. We would set that as our prior for that, and that would inform that value. But we'd still probably want to set our measure of effect as peaked at 0, just for sort of skeptical readers. All right. We'll continue on Thursday with a slightly different example of binomial data.